Okay. Hopefully people can hear me. If you can you guys put a comment in? I did test this before, but it's been a while since I've done one of these. So hopefully I set up everything right because it's been a minute. I'll wait for at least one comment. If I don't get a comment, I'll go anyways. But I'm hoping, fingers crossed, that you guys can actually hear me. Okay. Awesome. I think we're good. I'm gonna go ahead and get started. Welcome to anybody that can show up. Today we're gonna get through, well, hopefully, we'll see how far we get, but I'm doing some kinematics. If you guys have questions as I'm going through, you guys can just pop them in the chat. And then also too, if you have any topics kind of about this topic, maybe something I'm not covering, feel free to go ahead and also, like ask those questions. I may not get to them right away. I'll probably like take breaks and sort of pause at periods in time that kind of make sense to just look at some of those questions and kind of go from there. We're going to start by talking about vectors. We're going to look at vectors first because it's really kind of the foundation for a lot of the motion-based stuff that we see within physics. And it's also going to be kind of the setup as you get into things like forces. So understanding vectors, while it's not directly tested on the MCAT super often, it shows up in kind of enough, I guess, other areas of physics that it's worth understanding relatively well. In order to understand vectors, I think it's best if we kind of view them in the way that physicists sort of wanted us to think about this, which is really on our XY graph. When we have sort of like motion or forces or like whatever physicists are talking about that fits on like a nice grid that we can sort of put in these dimensions, sort of like straight up, straight down, sort of to the left and to the right, things are like relatively easy to describe, but things are not always going to be in these directions. We'll just sort of start here. We can define this in terms of like the X direction and then also the Y direction. So X direction, it's kind of just like anything along this x-axis. So that's your left and your right pieces. So that will be here. And then your y will be up and down. And then we look at things being sort of like negative as well as positive. And this is again in that x direction, like as we're going to the left, physicists describe this stuff as being negative and this stuff as being positive from a vector perspective. So if I was like gonna describe some line that's going to the right, we just give it a positive number because it's just easier. And if we were going to the left, we would just give it a negative because it's also just like easier to go ahead and describe as well. Same thing in the up and down direction. So if we come up here, what we're going to see is that in the y direction, as you go up, we generally describe this as being positive. And then in the down direction, we generally describe this stuff as being negative. So a lot of times, like what physicists are sort of like really looking at here is we're thinking about that typical kind of like XY grid that you would normally have and just defining and using signs in this way to give something a particular direction, which is like the whole point of a vector, is to be able to define the direction of something as well as how big it is. So when we think about signs, I think having an understanding of how signs are going to show up in physics later is really important. And you're going to see this in a lot of different ways. So if you understand the concept of signs in like kind of how we use a lot of the math in the context of whether it's like chemistry or physics, your life is just going to be a lot easier because these things that maybe don't make as much sense, like a negative delta G, like what does that mean, is going to start to make a lot more conceptual sense, which I think is really important. So like, for example, when we think about something like lenses, way down the line, and we're thinking about these signs, what we're going to see is that we just give a particular convex lens a sign that really just is telling us like, hey, this is this type of lens when it comes to its focal length. So this positive value right here is really just saying like you're dealing with this kind of lens. And when we come over to something like the diverging lens over here, we give it a negative focal length. And all that's really saying is that, hey, like this lens on this side is diverging. So these signs are really standing in for some sort of concept. In the other situation we were looking at right on our XY grid, it's telling us, oh, this is to the left, this is to the right, or this is up and down. Here we're sort of saying, oh, this positive is telling us that this is a converging lens, or this negative is going to be a diverging lens. Or if we look at kind of in chemistry, we're looking at some of our sort of like delta G values. What we're going to see over here is that we're looking at the direction, usually in energy. So if we come down in energy like this, like that right there is your negative delta G. And what this is sort of telling us is that we started at a higher energy and we're going to end at a lower one. So it's sort of telling us that direction of the energy change and where it's going. So in this case, like if we're thinking about it from a systems perspective, if this was sort of your system, well, like how do we go from something that's higher to lower? Well, we have to get rid of energy. And that's what that negative is really telling us, is conceptually it's saying get rid of. This is just the reverse, right? This is your positive delta G value because again, it's doing the same thing. And this is telling us we are going to gain or add into it. And we're going to see this sort of theme all throughout physics in a lot of chemistry. If you can understand how this stuff sort of integrates, I think it's going to be a lot easier to sort of see what's going on. And it ties into it, into a lot of this vector stuff, even though it doesn't seem to have a whole lot to do with like the very basic physics of like acceleration and velocity and things like that. I'm going to go ahead and kind of move on and talk about a little bit more about like, okay, we've looked at some of these signs. We're sort of seeing how physicists are describing it, like what is a vector, what's sort of going on, and how do we manipulate this and actually use this information for the MCAT. So like I was sort of saying, like it's really nice when things get defined in this very like up and down direction or to the left and right direction for problems. But obviously, like when we think about forces, which obviously like if you are talking about a push or a pull, that's what a force is, we can get pushed forwards, but we could also get pushed backwards too. So we could talk about a positive push, maybe that's pushing us forwards, or that negative push, which is pushing us backwards. But these forces can also happen on sort of like a different direction. So for example, if we're looking at a ball that's just going to roll down the plane, right? The force that's sort of acting is pushing this down this plane like this here. And so when we think about this vector, if we're putting an RXY grid, it doesn't align anymore. And this means that we need to know what to do when a vector doesn't align on a nice grid. Like how do we actually manipulate these things? How do we work with them to also answer questions? To get at kind of this idea, I want to look at a little bit of a quick detour into some triangle geometry. If you'll just give me a sec, my dog has got a very loud toy. Okay, sorry, dog interruption. And so if we're sort of looking at this force, right, we could think about how strong is this force coming down this, and then we can break this into two different pieces that actually align with our grid. So we could come and say, okay, down, right, because part of this thing is actually going down, and the other part of this vector is coming over to the side like this. And what we're going to see is that these are going to form triangles. And all of your sort of like vector work that you're going to be doing is either going to be just in like straight up and down, left and right directions, or it's going to be coming into the concept of triangles. And if we don't understand triangle geometry, we're going to end up having a lot of trouble with vector style questions because that really is the foundation. So I want to take a little bit of a detour into some of these triangles. And before I do this, I want to answer one question about how long will this be? I'm actually not 100% sure how long this is going to take. In the past, lives have been maybe a little bit shorter than an hour. I imagine this will probably be in that same time frame, like an hour, hour and a half. But obviously, I mean, you can like dip out whenever you want. So what we're sort of seeing here is right this triangle. So little detour into triangle geometry. And I want to try and hopefully instill a little bit more of a conceptual understanding of some of the things that we're seeing and how this material is going to kind of keep coming up in the future. So like while we're still talking about vectors and hopefully coming to an understanding of them, I'm hoping to prepare you a little bit for some of the future types of questions that you're going to get asked. So if we take something like a sign, like what is a sign actually sort of describing about a triangle? Like, yeah, we know SOHCAHTOA, right? Which is saying, oh, like the sine is the opposite over the hypotenuse, but okay, great. What does that actually mean? I mean, maybe you can like plug some stuff in and get something out at the end of the day. But what we're going to see is if we define this angle, we're going to look at it right here, and we look at each of these triangles, which is going to have a different angle. And what we're seeing is this right here, this is the largest angle. This guy's in the middle, and then this guy here is the smallest angle. And when we were thinking about this, right, this guy would be your hypotenuse. So we'll come and just label this on each of these. We won't really look at the hypotenuse here for a sec. And then we have his opposite. What we're saying is we're saying opposite of this angle. So this guy here, this guy here, this guy here. So what we see, right, is as we decrease this angle, as this angle shrinks, right, it gets smaller, 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 this opposite side is also getting smaller. Another way of saying this is like the sine of a particular angle is going to be directly related to that side that it's describing, that opposite side. All that's really saying is just like, hey, like if your theta value is going to get bigger, then that opposite side is also going to get bigger with these triangles. Okay, like how do we actually use this? Why is this important? We're gonna look at a kind of, not an actual inclined plane question, but a question that kind of is helping us understand like how could the MCAT actually test this material when it comes to some of these like triangle geometry stuff and where the vectors are going to come in. So see, this one here says that if there are no net forces in an inclined plane problem, then the parallel force down the plane will be equal to the frictional force. So assuming there are no net forces at all angles, the same box placed on a plane set up at which of the following angles would generate the largest frictional force. And then here, this is just the equation that you would have for your force parallel, which is like the force going down the inclined plane. So if I just draw this problem out here, what we're gonna have is a box like this, and this would be coming down. So that's our little vector here, our force vector coming down the angle or down this plane like this. And now we want to know, okay, great. Like if we're sort of looking at these different angles, how do we make this the largest frictional force, given that it says that what we're going to have is that this parallel force will be equal to the frictional force? Really, what we can say is how do we make this force as big as possible? Well, here's what we know. We know that if this is sine theta, right, if we go back to what we were looking at before, is that as this theta value is getting bigger, this O value is also getting bigger. Or another way of thinking about this is like whatever these two things are equal to, whatever that sine theta is controlling, it's going to cause the opposite thing to also get bigger. So in this case, that means that as our theta or our angle value goes up, our force parallel will also increase. And as a result, the force of friction in this case, because I just said, right, in this particular problem, that they are in fact going to be equal. So we're looking at a problem like this, we would just pick the largest angle. And the whole point to kind of like the main thing I'm trying to teach you with this particular one is just a more conceptual understanding of what a sine theta value is sort of doing and how that's controlling a lot of the things on the triangle. So what we were seeing there, right, is like as that angle was getting bigger, 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 we're seeing that opposite side expand, 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 expand. The same thing here, right, is like as the sine theta value is getting bigger, this force of parallel is getting bigger, 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 bigger. And to some degree, this should make sense because if we look at this at an extreme, which is really just like a straight up and down line, because here we're at 90 degrees, it's really as big as this thing can get. Well, this is just pointing straight down. So remember from our vector perspective that we were looking at before, like this angled sort of force was split into two things. It was split into one that was down and one that was to the right. Well, now this is just like straight on our XY grid. So if we're just coming straight down, we're going to get the biggest that we can get. Hopefully this makes a little sense. And if you think about a lot of those equations that maybe you've seen or you're studying that have a sine theta value in them, you can now connect like, oh, like that means that as that sine theta value is going up, like I'm seeing an increase in that particular value. You see it in something like Snell's law later. It's like n1 sine theta 1. Oh, like as that angle goes up, that sine theta value is also getting bigger. And you're going to start to see on the opposite side, like, okay, if this side goes up, then the other side, something's got to change so that this is going to be sort of equaling out. So then I want to go ahead and flip and think about, well, what about cosine theta values? And again, we're going to sort of do this exact same thing. We'll think about SOHCAHTOA, right? So this is now the COA part. So that's the C adjacent hypotenuse. Basically what this said is like, hey, if you find some angle, we're going to go ahead and call it this guy here. So this will be our theta, and then our theta. And in this case, we're seeing something a little bit different. So this guy is the biggest. This one's in the middle. And now this theta is the smallest. Come and label our hypotenuse. So same thing, hypotenuse, 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 hypotenuse. And then now we're going to go ahead and look at our adjacent. So if this guy was opposite, when we say adjacent, we're talking about a thing that's like right next to it, but not the hypotenuse. So here's your adjacent, adjacent, adjacent. And now what we see is like this is exactly opposite of what we saw for the sine values. So when we come over here, we have a really big theta value. When we take the cosine and we look at that adjacent thing, it's getting smaller. And then as that angle gets smaller, the adjacent side is going to get bigger. So if the sine value that we were looking at was going to be direct, the cosine value will be inversed. And so now what I want to go ahead and do is look at another sort of aspect of this inclined plane and see here. So this one asks us, on inclined plane, a box experiences a normal force equal to the perpendicular force. When sitting on an inclined plane, the box will experience the lowest normal force when the plane is set at an angle of blank. So again, if we have this inclined plane, so we're going to just go ahead and think about this here. The angle is like this. If we look at a perpendicular force, that means just perpendicular to the surface or pointing straight in. So again, we're at this sort of like awkward angle. We're not in our nice XY grid, which is why we're seeing something like the cosine value pop up here, because that's just like how vectors work, right? They turn into triangles, so we need to be thinking about the triangle math. If we break this guy up really quickly here, it's going to have something that's pointing down like this, but also a little bit sort of pointing like this. This is how we would get to this particular guy here, or we could look at it from the other direction, but this is fine. So when we're looking at this, we say that the normal force, this guy's perpendicular, will be equal to this. And in this case, right, we're given this cosine theta value. We know that these guys are inverse. So if we want the lowest normal force, like the least normal force or the least amount of pushing into this box, well, if that's going to be related in this instance to a cosine value, we know that these will be inverse. So as this theta value is going up, we know that the force normal will be going down. That's just the inverse relationship that we were seeing before because of how the triangle geometry ends up working. So if we want to come and look at this one here, we would say that our answer is going to be 0 degrees in this instance. And again, if we think, 80 degrees. And if we think about this here, this is going to make sense because if we go back to that 90 degrees, which is the extreme, if we look at this, right, this is the biggest angle that we're going to get. Well, we don't push into this at all. Like that doesn't exist. And so what we're going to see in this particular case is that, of course, right, we're not pushing into this at all. So the main takeaway from these two questions here, right, is that when we think about some of our vectors and how this shows up in future questions or future equations, when we see things like cosine or we see things like sine, we want to think about these proportionalities. This helps you understand a lot more of those conceptual questions. So I'm going to go ahead and kind of step away from this for a second and just like think about a particular problem that we could kind of just like ask really quickly here to think about another application of this particular idea. So let's say we're thinking about torque, right? Something completely different. The way that torque works is it looks at the cosine theta of how like some sort of force is coming in. So we can begin to think about, okay, sorry, I said that backwards. If we look at the torque, we're looking at the sine of this value. So sine theta value. So if we're thinking about like, how does this work? Okay, so like where will we have our greatest torques? Okay, at our greatest angles because we have that sine theta in there. And vice versa, right? Like if we want to figure out where are we going to have the smallest torques from an angle perspective, okay, that's going to be at the smallest ones. So you can see how manipulating some of these vector concepts, the sort of, you know, cosine and sine stuff, how that helps us with some of those more like conceptual questions or proportional questions on the MCAT. Hopefully the concepts around the sine and cosine sort of make sense. If anything isn't clear, go ahead and like pop some of this stuff in the chat and then I'm going to kind of be moving on. But if there is some confusion or people are a little bit unsure, they want some clarification of sort of how we think about those angles, then I'll try and wrap back around to it as we sort of like get through some of the other concepts with the triangle geometry stuff here too. When it comes to vectors, right, we may have to actually go and solve out the values. And I think a lot of times people are in this sort of space of like, okay, I just talked about all the SOHCAHTOA stuff like the sine and the cosine. Like I'm going to go and memorize a bunch of these values. Like we're going to go and we're going to memorize what is the sine of 30 degrees? What is the cosine of 30 degrees? What is the sine of 60 degrees? That might be worthwhile. I don't know like how often you're going to use it. I think if you do have time, it's probably worth memorizing, but it's pretty low on my list. I actually think things like special triangles, which is what we're going to talk about next, are going to be a little bit more important. So when it comes to special triangles, we're not going to go crazy here. You know, this is not the GRE. We don't need to learn like all the special triangles. We're really just going to focus on two. So the first one here is what's called the 3, 4, 5 triangle. And basically, the way that this guy works is just if you have things in this particular proportion, so you have one side is 3, one side is 4, then you know, so long as it's a right triangle, that the other side is going to be 5. So for instance, let's say we have this ball, and this ball is going to get pushed to the right 6, and then it's going to get pushed up 8. And let's say that what we want to know is like, what was the straight line distance from where it started to here? And now we can see that this is forming a triangle. We have a little triangle here, right? It is a 90-degree triangle. And this is an example of the 3, 4, 5 triangle, because this guy, right? This is 3 times 2. This guy is 4 times 2, which means that this guy over here is going to be 5 times 2, or 10. Like, yes, you could go and you could use Pythagorean theorem to solve this problem, but if you can recognize this pattern, then this is going to be a lot faster. And you might be saying, okay, great, Chris, whatever. Yeah, I'm not taking the GRE. This is the MCAT. Do they actually, bring this stuff up? Is this actually something that the MCAT does? And I would say yes. Like on the section bank, we actually see an example of them using this special triangle. There are reasons for it. One is like special triangles are one of the ways that the math actually works out to be relatively easy using Pythagorean theorem. So they're going to pick math that is realistic. So if we can come in and learn this triangle, we can be a little bit faster. We can be a little bit more efficient when solving these sort of vectory problems because, again, they're just triangles. Okay, the next one we're going to go ahead and look at here is going to be the 30, 60, 90 triangle. And this is, again, going to be a right triangle, right? Because we have the 90 degrees there. And with this one, what we're going to see is that we're going to have the angle set up so that one is 30. If one is 30 and it's a 90-degree triangle, the other one has to be 60. And what we're going to see in terms of the ratio here is that the hypotenuse is going to be 2x. This side over here that's across from the 30 will be equal to x. And then this one that's across from 60 will be x square root of 3. Now, solving, a x square root of 3, like 5 square root of 3, probably not super realistic. But this relationship between the hypotenuse of 2x, right, that's your 10, and your x value over here, which is going to be your 5, like that is a realistic thing. And that is something that I have also seen on some of the actual AAMC MCAT material. And so we know that this is a realistic thing to kind of pay attention to. So again, how do we go about using something like this here? Well, again, let's go ahead and sort of look at an example problem really quickly, obviously just with a triangle. So what do we see here? Obviously, we're not given all the angles. That makes sense. The AMC is not always going to give you all the angles. But what we have is we have this 30 degrees. We can see that this is, in fact, a 90-degree triangle here, which means that this top one is going to be 60 degrees as well. So if we're looking at all of these, we have our 30, 60, 90 triangle. Well, what do we know about the 30, 60, 90 triangle? Well, we know our hypotenuse, which is that straight line distance, this sort of yellow arrow right here, from where this is starting to x. That guy, that distance, will be 2x. And we know that across from the 30 degrees, which is 8, this guy is x. So if we want to go ahead and figure out how long is this distance from the ball to where it ends up in a straight line, that guy will be 16. It's just going to be 2 times whatever the x side was, which is 8. So 8 times 2, this guy will be 16. So this is another example. We're going to get into some actual application questions where we're going to have an opportunity to actually spot these patterns and see how the vector questions are going to work. But hopefully the actual sort of geometry review here is making sense. And of course, the last way that we could go about solving these problems is, sort of the OG Pythagorean theorem. Hopefully you guys are like relatively good with using it. We're going to go ahead and just look at an example. And the main time you're going to use this is when you don't have any of those patterns, right? This is not a 3, 4, 5 triangle. It's not a 30, 60, 90. Okay, fine, AAMC. You're making me do Pythagorean theorem. I'll do it, right? Hopefully we know this guy is going to be a squared plus b squared is equal to c squared. C squared, this guy right here, that is going to be your hypotenuse. And then the a squared and the b squared, these are just the other two sides. So if I take 8 squared plus 5 squared will be equal to c squared. So that's 64 plus 25 is equal to c squared. So if we add these two guys up here, we're going to go ahead and get 89 is equal to c squared. Take the square root of both sides. square root of 89 is equal to c. So we know that the hypotenuse in this case would be equal to the square root of 89. With this case here, what you can realistically do is just sort of like take your best guess as to where this is. I just like to do this by just figuring out, okay, like what are my sort of like two closest square roots that are nice and easy. So one of these guys is going to be the square root of 81. That guy is equal to 9. And then we have the square root of 100. That guy is equal to 10. So what's the square root of 89? Somewhere kind of around 9, a little bit closer to 9 than 10. So if I want to just estimate this guy, I'd say maybe like, I don't know, 9.3. I don't know what the exact value is, but this would be sort of how we're going to look at some of these vector questions from the perspective of using something like the Pythagorean theorem. So really, just to recap, we sort of looked at this ends the sort of triangle geometry sort of recap that we have here, which was going to be, right, you have your first special triangle, the 3, 4, 5. You have the next special triangle, that's going to be your 30, 60, 90, and then you have your OG, just like Pythagorean theorem. If all else fails, you can go ahead and always revert back to Pythagorean theorem. It will work. It's just less efficient. The other versions are going to be a lot more efficient if you can spot the pattern. Okay. So if we come back right around to sort of what we're seeing, hopefully we have a much more robust understanding of when we're looking at this vector that we can just turn it into a triangle. And we have all of these different ways of dealing with this triangle, right? We could say, oh, well, this is a 30, 60, 90 triangle. So if you want me to define one of these pieces, I can do that. Or we could say, great, well, if this is A and B and C, and you want me to find C, and I have A and B, well then great, I can go ahead and just use the Pythagorean theorem. Or maybe it turns out that this is one of those special triangles. So maybe this is 3 and 4, and then we know that this guy is 5. Now, so far we've sort of just talked about triangles, and we've talked about some of the vector pieces. We've seen sort of like taking something that's at an angle and describing it in terms of that triangle. But what if we have multiple ones? Because that's realistically how a lot of vectors work, is we're not just dealing with like one thing. Yes, we're looking at, different directions of like maybe this ball is not going straight up or straight to the side. It's sort of going off at this angle. But that's, in my opinion, not often how the MCAT is going to ask a lot of these vector questions. They're going to ask you to actually add vectors together. They're going to ask you to subtract vectors. How do we do this? Well, I think the easiest thing to think about is let's forget about the fact that this stuff can be on an angle. Let's just think about things going to the left and the right. So let's say that we're sort of playing tug of war on this ball. We have this ball in the middle, and one group sort of pulls to the side. And let's say they pull with some 10 units. I don't really know what 10 units is, but it's 10 units. They pull to this side, and somebody else pulls to the other side with 10 units. Well, in this case, nobody's going to win. The ball is just going to stay exactly there. And what we're seeing, right, is that, okay, the pull to the left and the pull to the right, they just cancel each other out. How do we figure this out? Well, I mean, it's sort of conceptually obvious, but a lot of times they talk about using something like the tip to tail method, and it works here. So when we say tip to tail, what we're sort of saying is we're saying, okay, take the tip of one of these things and align it with the tail of the other. So if I did that here, it would just be an arrow that is going from this guy right here back to where we started. And generally speaking, what you're going to do is you're going to look for, okay, how do I get from this starting position, which is right here, to the ending position at this other one? Well, we're already back there. Now, in this other circumstance, let's say it's sort of the same thing, but these two groups of people decide to work together. So now we're just pulling to the right in both cases. So this one ends up being 10 and also 10. Well, again, we can use the tip to tail. I mean, you don't really need to. We can just be like, great, cool. We know what happens. This ball is going to get yanked this direction at 20 units, whatever my units are. But again, how do we come up with this? Let's go ahead and say that this first guy here is going to be the yellow arrow. So if I was to put my yellow, we'll come to here. And then we'll go ahead and label the second one with red. So if the first one was 10, it was the 10 plus 10. Pretty straightforward, nothing crazy. And what we're seeing here is an angle difference between these two things, right? So like these guys right here, these end up being, how are they oriented? Well, they're oriented one after the other. There's actually no difference in their orientation. So the angle between them, we would say, is 0 degrees. If we were to come over here and look at these two, the angle orientation between these two would be 180 degrees. Because if you think about a circle, like this here, if this is your 0 degree mark, this is your 180 degree mark, these guys are completely oppositely opposed. So if 0 is pointing like this, 180 would be pointing like this. And again, if you're at 0, you're just pointing in the exact same direction. Okay, so Before, this was relatively easy. All the numbers were the same. What if the numbers are not the same? Well, we're just going to use the tip to tail method again. It's relatively easy. And again, I think this question is pretty straightforward. What we're sort of seeing here is, right, we have the 8, we have the 4. They're obviously in the opposite direction. So what we get, well, we know that the 8 side is going to win. 8 side is going to win. We're going to pull this direction. We're not going to get all of it. Some of it's going to be canceled out. And so we're going to only get a total of 4. Again, using the tip to tail method, just put this guy here. So here's our tip. Here's the next tail. It's got to point this direction. It's 4. How do we get from our start, that's right here, to our finish like that? Well, we're going to go this direction. How much? 4. Because that's what would make up what we're seeing here. Again, hopefully not too bad. Now, where things get a little bit more complicated is going to be something like this, where we have angles, right? So before, everything was nice. It was on that beautiful XY grid that scientists really like to use. But what happens when we are not at XY grids, and how is this stuff going to sort of show up or be sort of tested on the MCAT? One way is, let's just go ahead and change this particular problem here. And let's say that this was an electrostatics problem. So what we're going to have is in the middle, we have a positive charge, and then we have 2 negative charges, one here and one here, and they're both pulling on this thing. And so what we want to know is, let's go ahead and come in and predict, where will this move? It's a question very similar to this on some AMC material. So where is this thing going to move? Well, when it comes to kind of your first approach for these types of problems, I would highly recommend just making a prediction. Just think about this and sort of think about what makes sense. The easy way to do this is, let's just go ahead and think that we have this sort of angle that separates these two here. And what we're going to do is we're going to do our very best to cut this angle straight in half, like this. So now I have a nice line that's right in the middle. And remember from before, when we were playing our tug of war, right, the larger pull ended up winning. And this is going to be the exact same thing here. So let's say that this arrow length is going to go ahead and represent the strength of the pull. So this guy, to me, this one looks larger, so it's going to be a larger pull. And this one over here is a little bit shorter, so this is going to be the smaller pull. Well, if all else were equal, like these exact things right here were pulling with the exact same strength, then what we would expect to see is that it would just get pulled straight on this line that I've drawn halfway between these two. But we know that the pink is larger, so if we wanted to come and make a good prediction about roughly where we would expect it to be, we should say, okay, well, it's going to be right or a little bit over to the pink side from this particular line that we've sort of put in the middle. So maybe something like this would be our prediction. So we make this prediction. Now, if we want to get more technical, we can go ahead and use the tip to tail method. And I noticed when I was reviewing these slides, made a little bit of a mistake on this one. So we're going to have to fix that really quickly here. This yellow line actually ends up being a little bit longer than it is. So we're going to go ahead and just sort of cut that down. And what I've done here is I've just gone and put in these guys from tip to tail. So we see here, right, we're starting. Say this is our sort of start point. We take this guy, we've got its tip. It's aligned with our pink thing's tail. And we're going to end up here. And if we come in and we draw the tip to tail direction, this is the actual direction that this thing would get pushed. And again, if we sort of put this onto our estimation, this is what we get. And what we've done so far, this is called vector addition. This is vector addition because we're adding up these two vectors to form what we call a resultant vector. So if we had vector A and vector B, and this is vector C, the way that this could be presented is we would say something like, okay, vector A plus vector B results, or will give us the resultant vector of C, vector C. Another way they could put this in there would just be A plus B will be equal to C, and they would describe this as being vectors. They're not going to just sort of like make you guess that you're dealing with vectors here. Like they will actually tell you that you're dealing with vectors. Okay, what about vector subtraction? So everything that I've been sort of describing so far, right, that was our vector addition. What about vector subtraction? How does vector subtraction work? Well, let's go ahead and think about subtracting this yellow one here. So before, what we had was this guy right here. And we know that, let's call this guy, I believe I said it was, let's look, B. So if this guy is going to be plus B, a little bit arbitrary on my signs here, but let's just go ahead and call this plus B. then we know from before, minus b, what is that doing? It's just flipping its direction. Because if you thought about the xy grid, that we were looking at before, right? If we had something on this minus side and it was going like this, plus side, then if we want its minus version, we would just flip this around so that now it's going to poke over on the minus side like this here. So if we want to do the exact same thing, and this has been defined as plus b, and we want to come over and look at the minus b, well, here's your minus b right here. So with these ones, what you have to do when you want to do vector subtraction is you have to define the opposite of what it is. And again, what I would do is if they were asking you for a rough direction, is I would just come in and I would make that guess. And again, I'm going to do that same thing. I'm going to define that sort of middle line. I see that the pink one is bigger, so I know that the actual overall direction will be slanted or slightly biased that way. Or again, you could set this up as a tip to tail method like this guy here. So we're starting right here. It's our start spot. We're going to end all the way over here. And what we're going to see is that I've taken this tip and I've put it at this tail. And if we come and we draw the final thing that we're going to get, it looks like this, which is not too bad, right? It's a decent estimation. In this case, it's getting larger. It's getting larger. And the other one, right, what we can sort of see here is this guy is a little bit smaller. And that's because we're getting pulled in opposite directions. This guy here, we're getting pulled in the same direction. So the stuff that is going this direction to the right is going to get added together. And it says, when doing the tip to tail method, how do you know which arrow to put at the tip or tail and at what angle? So I would say that it actually doesn't matter which arrow you choose to put at the tip or the tail, so long as you make sure that you put these at the tip or the tail. So if I kind of like come back to this first one that I did here, let's say that I just happen to choose to put the reddish or pinkish arrow down first. That's totally fine. And then what you can do is you can come in and make sure that you align the other one at the tip to tail and then just like go ahead and draw this. So for example, if I come in here and I'll just like start with my sort of like reddish pink arrow. Actually, let me just change the color so that way it actually looks distinct again. So we'll go ahead and just put this guy here. Roughly something like that. And then we're going to come in and just make sure that the tip of the yellow one is going to end up here. So the tip of the yellow one is going to end up here. We're going to come in, probably not going to do the best job. There's my sort of yellow one. And then again, right, so long as you measure from where you start to where you kind of end, you should get roughly the same thing. Now, obviously, I have not used the exact same spacing here. So this is not looking exactly identical, but they're pretty close. So you can sort of see what I'm saying with this. And then it says like, how do you know at what angle? So what I would say is with the angle, I personally just wouldn't stress about the angle. Why? So in physics, that would have, like in your physics class, like that really would have mattered quite a bit. But for something like this here, like your MCAT style questions, they don't get so precise about having you actually solve the angle. The majority of times, what they want you to understand is just that, like, okay, if you have a larger pull to one side and they're pulling sort of in opposite directions, that it will be skewed or slanted towards the larger thing. Like that is, in my opinion, the main thing that matters for the MCAT. So I would say like you can just like do your best to sort of just like sketch these lines out at roughly whatever a diagram is sort of telling you. Hopefully that helps and kind of answers that question there. We're going to go ahead and look at some actual practice problems. Some of these are sort of modeled on the way that the MCAT answer these questions. And if there are follow-ups to that question that you did ask, after we go through these, we can hopefully kind of wrap back around to them. Okay, so this says, what angle would produce the smallest resultant vector between vector A, which has a magnitude of 5, and vector B, which has a magnitude of 7? So obviously, it does not tell us the angles here. All we know is that we need to produce the smallest resultant vector between these two particular numbers. Now, there's all kinds of angles that we could sort of place these at, and we don't want to go ahead and start to just like try angles randomly and just sort of see, what about this one? What about this one? What about this one? So what I like to do for questions like this is I want to just pick two things that are sort of like representative or kind of extreme. So for me, that would be, what if we put these things at 0 degrees? So if this is our sort of triangle, or sorry, our circle like this, And what if we put them at 180 degrees? Because remember, these guys are going to be in the exact same direction. So this will be 1 of 5. So we'll make this guy 5. And then 7. 7 is going to be a little bit bigger. Or we could say, what if these guys were at 180 degrees? So that would be 1 sort of pointing like this. Say those guys are 5. And then our 7 pointing like this here. So if I come and I look at this guy and I use my little tip to tail method, what we're going to see, this guy is 5 matched up with a 7. So if we go from start to finish, boom, up here, these two things are just going to get added together. So it'll just be 5 plus 7 for a total of 12. So this guy would be 12. And this guy's probably not going to be the smallest resultant vector because we literally just like put these things so that we'll point in the exact same direction and add up. That's probably not going to do it. 180 on the other hand, if we come here and we do that same thing, so we have a 5, kind of like this. And again, tip to tail, so I'm going to go ahead and take this guy's tip, put it to the tail of our 7. Here's where we started. Here's where we end. We're going to look at this. This guy is going to end up being 2 because there's going to be the difference between these. Now, these are the two extremes. So what we have is we have 0 degrees, right? That is the very smallest angle. You can't get smaller than that. And 180. Now, you might say, oh, well, like, couldn't you be at 360? You could be at 360, but that's actually just coming back around to 0. So these are your sort of like biggest differences that you're going to have. Even if you come at something like 270 degrees, realistically, what you're looking at is you're actually just looking at a 90-degree difference between these two things. It is not 180 degrees. So 180 degrees is the max that you can get. So what I did is I looked at the two extremes, and what we can see is that this guy right here, this is going to be the extreme on the small end of these vectors. This guy is actually going to be the extreme on the big end of these vectors. So if we wanted to think about the range, because we can come at any angle of the possible vectors here, we would say it's somewhere between 2 to 12. Because this guy is our 180 degree and our smallest. And this guy right here is our 0 degree and our very largest on this end right here. So what angle would produce the smallest resultant vector between these two vectors? Well, that's going to be 180 degrees. And it will always be 180 degrees. That's never going to change. If these were, I don't know, 5 and 10 or 12 and 15, it's always going to be 180 degrees between these two things, giving you the smallest, and 0 degrees giving you the greatest. Okay, we'll go ahead and look at this next question. And we're going to go ahead and think about this. We're going to have to combine some things, and hopefully this will teach you a little bit more vectors as we answer this problem. So here we have two vectors. We have vector C, we have vector D. We're told that vector C has components Cx is equal to 7, Cy is equal to negative 12c, and then we have vector D has components Dx is equal to negative 1, and Dy is equal to 4. Okay, so we're looking at this. We have these two vector components, and what they've done is they've broken these out into the x's and the y's. So if we're thinking about our coordinate plane, we're going to go ahead and draw these on there, which is the first thing that we're going to do. So here's our coordinate plane when it comes to our vectors. Let's go ahead and pick some colors for these guys. Let's go ahead and make vector C pink, and we'll go ahead and make vector D yellow. Now we know, right, x direction, that's our left and our right. Doesn't actually matter which direction you go with this. This is going to be the typical one here. But for 7, we're going to come like this. We're going to go ahead and call this guy 7. And now we have the y component of this, and that is negative 12. So that's going to be in our up and down direction. And now what we're going to do is we're going to come down like this, negative 12. Now we're going to look at vector D. This has components of dx minus 1. So again, that's going to be in our x direction. It's going to be to the left now, so it has to be opposite of the 7. So coming here, that is going to be this direction in 1, because remember that negative, right, just gets turned into a direction. This positive, which we can't see here, that's that direction. This negative right here, that was the down direction. So the magnitude is 1. That's all that's showing up here. And then lastly, we have our y, which is going to be 4. So this guy right here. So now it says that sketch the approximate resultant vector r equals c plus d on the coordinate plane. So now what it's asking us to do, it's asking us to go ahead and add these two particular vectors together. Now, I don't know about you, but all we have is just a bunch of things that are sort of pointing up, down, left, right. That really doesn't look very similar to what we were dealing with before, right? Before, what we had was this very nice, like, oh, you have a line that's sort of like going off this direction, another line is sort of going off this direction, and we could sort of make a decision about where in this are we pointing. Are we pointing sort of like this? Are we pointing sort of like this? And we could estimate that. Now, we have a couple of options here. One, we can use the tip to tail method to figure out what these x and these y's actually create. Because if you remember back to what we were talking about before, sort of show this, so that way we can be a little bit clear here. When we were breaking this guy out, we just made a triangle of it, right? And we can do the exact same thing. We can actually go in reverse, right? We can take this triangle that we made right here out of this vertical thing, and we can reconstruct the actual sort of diagonal component. So if I do this for the yellow one, we're just going to use the same tip to tail method that we would do before. So this was up 4 over 1. So the resultant, or the angled version, would be something like this. Sure, we don't actually know how big it is, but this is what we would see. And then for our pink one, we can do the same thing. We know that it should point 7 like this, and 12 down like this. Except that's wrong, because we should put these tip to tail. There we go. And so we would get this diagonal that is something like this here. So now if we're looking at sort of what we have, we can begin to see that it looks like to me that these are sort of pointing off at opposite directions. You can imagine if we were to just sort of come here and add in a little ball and move this guy, maybe give ourselves a little bit of a highlight so that we know what is the most important thing to pay attention to. It's going to be this line here, and then this guy here. If you want, you can make a predicted resultant vector between these two. Maybe something like this. So maybe I'm going to come in and say it's something like this. So this would be one way of sketching this sort of approximate vector that we have. But the other way that we could go about doing it is just realizing, okay, well, if we have broken everything into a nice x and y, well, geez, isn't this just like that tug of war that we had before? And this tug of war, this was really, really easy to solve. Because all we did when we were looking at these tug of wars is we just sort of said, well, are you adding up or are you sort of subtracting from one another? Same thing here, right? So when we did this guy, we said, okay, if you pull to the left with 8 and somebody else pulls to the right with 4, what we're going to get? Well, we're going to get a net pull to the left, and it's going to be with 4. So if we come back and we apply that particular concept on what seems like a more complicated question, it's really not, it's just putting these things together. What we could say is, okay, let's just deal with how this ball is getting pulled in the vertical direction, so in the y direction. So it's going to get pulled up 4. It's going to get pulled down 12. So what is our overall net here? Well, our overall net will end up being 8 down. That's the 12 minus the 4. That's at that 180-degree angle like we were seeing before, and so they're being subtracted from one another. Okay, great. So we can come in and say, okay, the actual resultant down will be 8. And now what we can go ahead and do is say, let's go ahead and think about this ball just in terms of its left and right pulls. And we know that it's going to get pulled barely over this direction, 1. It's going to get pulled quite a bit more over in this direction, 7. So what will be the overall resultant pull to this direction? Well, if we pull like this here, that is going to end up being a total of 5. Sorry, I can't do math. 6. There we go. Perfect. 6. And now, instead of doing this twice, right, we can just go ahead and say, great, I have this simplified down to just the net up and down pulls that we have. And if I put those together, I can sketch out my rough one. So that would be 6 this direction, 8 down, arrange these tip to tail. And there you go. Like that. That would be your approximate resultant vector on the coordinate plane. So now we have this last one here, and it says, let's calculate the magnitude of r. That is the actual resultant vector. So if we're looking at this here, that would be this guy. This is that one that we've been sketching out, that we've been trying to find. This is r. Well, what do we have? This is a 3, 4, 5 triangle. We may not be able to spot it because it's a little bit different, right? But this is 3 times 2. This is 4 times 2, which means that this last side, this guy has to be 5 times 2 or equal to 10. No need to do the Pythagorean theorem or make this any harder on ourselves. So hopefully you're sort of seeing how some of those things that maybe I meandered through a little bit are kind of coming together to sort of fit together to answer these types of maybe more complicated questions. hopefully this one is sort of making sense. And if people have questions, feel free to put anything out there. I know vectors can sometimes be a bit overwhelming. I'll keep an eye on the chat, and we're going to look at our last one for vectors here. Okay, so this time we have two forces of the same strength are pulling on a box at 60-degree angles. The 60-degree angle hopefully is going to stick out to us now. We should be thinking about our 30, 60, 90 triangle. We've been thinking about vectors this entire time, so that's what's coming up for me. And it says, as shown below, what must the magnitude of each force be to produce a 12 Newton force that pulls directly to the right? So a couple things that we know. We know that both of these forces are the exact same strength. So for example, if this guy is 10 newtons, this guy would have to also be 10 newtons. That's pretty easy. And then what we know is that we want them to produce a 12 Newton force that pulls directly to the right. So that means that whatever gets pulled this direction, this needs to be a total of 12 newtons. Yeah, I know, Prince is crazy. He's very cute, but I apologize if he's distracting and kind of disruptive. And this is what we're sort of going to see in this case, right? Is this 12 Newton is going to be pulling directly to the right. So how do we get this? Okay, well, we have to think about the fact that we have two of these, right? We know that they have to be the exact same, which means that the way that this 12 Newton is being made is it's coming from two things, right? So this is a vector addition question. It may not seem like it right away. So we know that part of this guy right here is pulling this direction. It's also pulling up. And then this one down here, which I'm going to arbitrarily put down in pink, is pulling this direction here. So this 12 Newton, that means that this guy has to be one component of it, and this right here has to be the other component of it, like this. Now, if these are both of the same strength and they're at the exact same angle, well, what do we know? We know that both of these things are equal. If both of them are equal and they're both together 12 newtons, this guy is going to be 6 newtons. This guy is also going to be 6 newtons. Okay, great. We know this side, and now we want to figure out this guy right here, right? This is the actual force. This is the actual pull. How big is it? Well, it's a 30, 60, 90 triangle. So let's go ahead and draw out what we had for our 30, 60, 90 triangle here. So this guy is going to be our 90. This guy, we're told, is 60, and this one is 30. Remember, your 30 side is going to be x. Your 60 side is x square root 3, gross math. This is going to be 2x. Thankfully, this problem was set up in such a way that it's actually not too bad. It's relatively easy to solve. Okay, yeah, right? So if this guy right here ends up being a pull of 6 newtons, and this is equal to our x, and our hypotenuse is 2x, or times 2 of this guy's going to be 12 newtons. So each of these particular pulls has to be 12 newtons. So this is 3 different vector questions. So hopefully these 3 different vector questions are starting to make a little bit more sense with some of the pieces that I was kind of pulling together in terms of describing all the different components and why vectors really just come down to understanding triangle geometry relatively well. I'm going to go ahead and take just a quick little pause, drink a little bit of water. If people have questions sort of at this point in time, I'm going to go ahead and just kind of wait maybe like 20, 30 seconds because after this, we're going to be moving on to some of the kind of like motion stuff, right? That's more of the kinematics. We have to have vectors kind of out of the way to understand some of the stuff, but we'll look at motion next. Not seeing any questions coming in. No big deal. I'll go ahead and just kind of move on. We're going to look at motion. And to understand motion, we have to understand what it is that we're actually kind of talking about here. I apologize if this is a bit bright switching to this particular screen. When we think about motion, right, we're going to have things that are vectors. That means they have a particular direction to them. That's what we have been talking about. We've been looking at those arrows and sort of seeing how long and in what way are they pointing. And we're also going to have things that don't really have a direction. It's just sort of like how long is something. When we look at this from a motion perspective, motion is going to be like how we're moving. Well, movement takes or is going to cover some distance, and it's also going to take some amount of time. And that's kind of going to be the 3 main things that we're looking at here. Now, our first distinction is going to be between what we call distance, and that's what we're seeing over on this left-hand side. This is distance. This is the actual sort of route that you took and how long in meters, or in this case kilometers, that thing is. Displacement is the other side of this. And displacement is that sort of you start and finish. So you're sort of at this X point, and where did you end if you were to just draw a straight line on this? So really all I did is I just went to Google Maps and I just said, okay, great, let's go from here to here and sort of look at this. And these are showing the exact same things. If I wanted to actually drive to this particular location, I would obviously have to go this entire route here. But if I wanted to think about this from a displacement perspective, which is just sort of how do I get there as fast as possible in a straight line, that would be this displacement piece, which is just, okay, draw a point from here to here. And lastly, we're going to see that this is going to take some amount of time to get from A to B. And it's really the combination of these things that we're looking at is going to describe your motion and on the MCAT. When it comes to a lot of this stuff here, to be entirely honest with you, in physics class, you wanted to be able to sort of like distinguish between distance and displacement. I'm not saying that the MCAT can't ask questions about this. We just have not seen them yet sort of ask these types of problems. And because we haven't seen them ask this type of problem, what I would say is it's good to know, but it's a little bit hard to give specific advice on like exactly how should you understand the application of this specific thing. So I'm not really going to get into that today. Just keep in mind that you have this difference between the distance and the displacement. We are mostly going to be talking about displacement today, which is the vector component of it, because we're going to be talking about things like velocity. Velocity is how fast you're going, but also in what direction, versus something like speed, which is just like how fast you're going. We don't care about which direction you're going in. Now, when we think about velocity, right, we get this sort of formula here. It's going to be the change in x over the change in time. So what is this really saying? It's sort of saying like how far did you go and how long did it take you to get there? So if I was thinking back to that sort of thing that I was looking at before, it would have been like, okay, it said it was going to take, I don't know, 13, 17 minutes to get from A to B. So if it was, I don't know, 15 kilometers and it took us 15 minutes, how fast would we be going? We would go 1 kilometer per minute. It basically breaks down the sort of chunk, if you want to think about this thing as a ruler right here. If this is your 15 kilometers, we can chunk this by time. So for instance, if we come here and we look at this, right, this is maybe minute 1 and you've gone 1 kilometer and 1 minute. So by the end, when you've done the entire 15 kilometers, you will have taken 15 minutes to do this. Now, why do I bother with this, right? Like, this is not a very difficult sort of equation to work with. I think one of the things that I see, especially a lot with the kinematics or this motion stuff, is that people are so focused on these equations that we sort of lose sight of what the question is actually asking. And many of these questions are much, much easier to solve and understand if we use a more conceptual framework rather than a sort of more explicit one. Can you give me a sec again? I apologize. I need to like save the poodle from the bed. Hey, come on. Go. Okay. All right. I'm going to go ahead and show an example of this. We're going to kind of jump ahead. That way this is going to make a little bit more sense. And then we'll come back and we'll look at some of these other slides that I have prepared. Prince, go lay down. So if we look at this here, right, we have a bacteria, right? It's moving at a speed of 1 millimeter per minute. How long in seconds will it take for the bacteria to go 50 millimeters? So I think about this little bacteria, right, using that sort of model, not using the equation here. Here's my little bacteria. Boom. Okay, how far is this going to go? Let's just say it's been 1 minute. And I'm thinking kind of about that sort of step that it takes or how I'm sort of chopping this down. So if I'm right here, right, it's been 1 minute. How far have we gone? We've gone 1 millimeter. Okay, what if we go another minute? Okay, so another minute, gone another millimeter. And what if we go another minute? Okay, here's 1 more minute. We've gone another millimeter. So in total, right, just after 3 minutes, we have gone a total of 3 millimeters. Okay, but how far did we want to go? We wanted to go 50 millimeters. So we could just say dot, 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 right? All the way out to times 50. And what we would see is that since each of these was a single minute, then what we would get is that it would take us a total of 50 minutes to get from where we started to 50 millimeters away. Okay, but we wanted this in seconds, and now this is just a matter of converting to the right units, right? We just take this and we multiply it by 60 seconds, since there are 60 seconds in a minute, and we will get that it was a total of 3,000 seconds. So in this case, like, I use that equation, right? I use the equation that I was sort of talking about before, that is the delta x over delta t is equal to velocity. I rearranged it because in that case, they wanted us to solve for t, so I rearranged it to get there. But you can see, if you understand it conceptually, there's not a good reason that you realistically need to use this particular equation. You obviously can, but I think a lot of these questions should make sense. So I want to show another way of looking at velocity, which is going to be a bit of a graph perspective, because I think a lot of people struggle with some of these graph perspectives when it comes to these questions. Okay, so let's go ahead and take, I don't know, a very simple line that we're going to draw here. And let's just say that we start at this point, and what we're going to see over time is that we kind of go up like this. So what's happening is that each of these steps, well, I don't know, let's just say that this is 1 second. And then we have 2 seconds. And then we have 3 seconds. What are we doing? We're taking a step and we're going some displacement. And then we take another step and we go some other displacement. And we take another step and we go another displacement. This is literally this line. We just took this line and we just put it on this graph. That's it. So if this was, I don't know, we'll just use our 1 millimeter. So this was 1 millimeter, 1 millimeter, and 1 millimeter. I didn't do a good job keeping these sort of like the same length, but for the sake of this, let's say that they all are ending up being the same length here. So what are we seeing? We're seeing this in the perspective of a graph, and if we want, we can figure out what is the actual velocity value. And this is one of the things that I think is kind of interesting, is that it's just the slope, right? Because if you look at this, this is saying, hey, take the change in x, okay, that's this guy, this is the displacement, and put it over the change in t. Well, what is that? That is the change in rise, because that's equal to the change in x, over, that's an s, let's make that an x. There we go, x, over the change in run, which is the change in t. So on this particular graph, which is a distance, or sorry, displacement over time graph, the slope right here will end up being your velocity. Okay, well then what's the difference between all of these graphs? Because all of these could be displacement time graphs. Why not, right? All of these can be displacement time graphs. Obviously, they look very different. And so we want to go ahead and think about what is making them different. And realistically, even though I'm talking just about displacement time graphs right here, you can think about any of these sort of like physics line graphs from the same framework that we're using, because the MCAT loves to ask these types of questions. So you can ask yourself, okay, they're asking me about this graph. Maybe the slope is important here. What is actually the slope? What does that stand for? You don't have to solve the actual value, but you can sort of ask that question of, what does it stand in for? How do I use that to help me understand what's going on? So in this first guy, what do we see? Well, we're stuck at one distance, and it doesn't matter how long the time goes on. We don't go anywhere. So what this is sort of saying is that we are just stationary. We are just sitting there. And this should make sense, right? Because remember, the velocity is equal to the change in displacement over the change in time. The displacement never changes. This guy is 0. Our velocity is 0, which means we're not moving, because the velocity is just whether or not you're moving or not. What about this guy here? Okay, well, what we can see is that obviously we have a velocity because our displacement is actually changing over time. Great, so it has velocity. Let's just say that. Now, what about over here? So this guy also has velocity because the displacement is changing, but there's a difference because in this first scenario here, it's not curved. Second scenario is curved. What does that mean? Well, when you have a straight line like this, this means that it's just a single valued slope. There is one slope value. It does not change. What about over here? That's not true over here because the curve, or sort of how quickly this stuff changes, it's going to be different depending on where you look. For example, if I come here and I sort of like roughly try and keep this the same distance, something I'm not terribly good at. There we go. We're going to see that the displacement increase is not the same. So here we came up by this much. But then when we came here, we came up by a larger amount. And then when we come here, we're increasing by an even larger amount. So realistically, there's actually lots of slope values. Okay, what does this mean? What does this mean? So in this first one, we know it has velocity. We also know this guy has velocity. There's only one slope value. That means that this is constant. So if you see a straight line like this slope, whatever the slope is, in this case it happens to be velocity, we can say that this would be a constant velocity. Now here, because there's multiple slope values, whatever this slope stands for, obviously it has velocity, is changing. So over here, we would say that this is a changing velocity. The velocity is increasing, decreasing. We'd have to figure that out. Okay, now let's go ahead and look top and bottom and think about what are the differences between the graphs on the top and bottom, because realistically, looking at them, they're the same thing, right? They're straight, they're curved. So why are they different? How do we read these? So in this first one, this is just sort of telling us that we're at a different spot. So if I was sort of thinking about how we could be moving, let's just say that we're rolling a ball along the ground, and we're doing it on a number line. Number line is just to make our lives easier here. Here's our number line. We have a couple of tick marks like this. We can go ahead and just give this some sort of random numbers. We'll call this guy 0, 1, 2, 3, and 4. So this can be 1, 2, 3, 4. 1, 2, 3. So in this first scenario, get this guy, can be our little pink ball. This guy's just stuck at 3. This one here, this one's stuck at 1. So they're not moving, and they're just right there. One is at 1, the other one is at 3. Cool. What about in this scenario here? Well, we've got to go back to our vectors, because this guy's a positive slope. This is a positive slope because the slope is increasing. As you go over, you go up, right? So those are both positive values, up, over, up, and over. Now here, this is not the case. This guy is a negative slope because it's pointing sort of down. So it's pointing down to the right, right and down. Well, that's just talking about being in different directions. Because remember, the signs values, going back to the vector stuff that we sort of first talked about, signs have meaning. They tell us about the converging and the diverging lens. They tell us about whether or not we have a spontaneous or non-spontaneous reaction, whether that system is getting rid of heat or if it's gaining heat. Here, this is just sort of telling us, are we, as we're traveling, going in one direction, or are we traveling and going in the other direction? So again, if we were on a particular number line, just like before, let's say that this guy is starting at 4, this one is starting at 0. If I was looking at this, here's 4. We're going to start here, and we're going to travel, and we're going to go this direction to 0. But if we were here, what we'd be looking at is we're at 0, and we're going to travel up. Say this guy ends at 4 to 4. That's the only difference between these particular ones when we're looking at the displacement in this case. Now, this last one is kind of interesting because the overall slope of both of these is positive because it points up and to the right. That guy's up and to the right. That is up and to the right. Sure, yes, it curves, but if you look at the sort of start and the end, we're up and to the right. So what's different? Well, let's go ahead and make these sort of same little tick marks that we had before. So there's this first one. There's this one, and then this one here. And let's sort of just see how these things change. So we came here, and we went up by this. Whoa, this was relatively small, right? This was a relatively small x increase, and this one is a relatively large x increase. Okay, now we come here. Okay, I mean, these are getting closer together. And now let's go ahead and look at this here. And then, whoa, big difference, right? This was a relatively large displacement or x increase. And this one right here was a relatively small x increase. So what is this telling us? Well, this is telling us that as we're looking at these velocities, because remember, the slope is the velocity, that in this circumstance here, we started off at a really high velocity and we got slower over time, which is why it kind of looks like that. It tapers out, right? It sort of like goes and then slows down. And the other one, on the other hand, sort of starts slow and then kind of, as time goes on, up and to this side. So basically, what you want to be able to do is look at a lot of these graphs and understand, okay, if I see something that is just straight across, the two things, there's no change in one of them. If I have something like this, it's changing, but it's constant. And whatever that slope stands for, that's the thing that's constant. And if it's curved like this here, what are we going to see there? Well, we're going to see that that thing is changing. If it's curving up and sort of shooting off to the sky, we know that it's getting faster and faster. And if it's not doing that and it's sort of like petering out, we know that it's starting off really fast and then it's slowing down as this is sort of going through. Okay, so far what we've done, right, is we've looked at velocity from the perspective as a distance over time graph, right? So these were the distance over time graphs. And just again, this is having no velocity. This is having a constant velocity. This is having a increasing velocity. Well, what if we looked at this a little bit differently and said, let's say that this is going to be a v over t graph now. So we're going to look at the actual velocity values in this case. Well, let's take this first one. This one's going to be the one that's in red. We said that we have no velocity. Okay, well, if this is measuring velocity, then we need to put our velocity right here at 0. And it never changes because there's never a velocity. Check, done. All right, what about this one? We know that this is a constant velocity. So how are we going to have a constant velocity? Well, it has to have a value. It has to have a particular value. Let's just make up a number for this slope. Let's just say this slope happens to be equal to 5. So this would be a velocity of 5 meters per second. And we know it's constant. So if I was to come on here, I would come up to 5 meters per second. And it never changes. It always stays as that. So this is kind of interesting. Now what we're seeing is that we're getting a different line when we switch to the next graph. So what we see is that if you have no velocity, you just get kind of the same looking line, but it's sort of all the way at the bottom. If you had a constant velocity, when we look at the v over t graph, now what we're going to have is going to have a straight line because it's constant, it doesn't change. Now, what if we come over and we do this green graph? Well, we actually can't be 100% sure exactly what this would look like, but we know that our velocity is going to change. So I'm going to just go ahead and draw this guy as a straight line. That's not necessarily what it would be. I'm not going to get too into the weeds as to why this would be, but this is what we would go and see is that we have to have some sort of changing velocity because that's what this was telling us, that it was an increasing velocity. And so our velocity, therefore, has to increase. So maybe it started at 0 meters per second, and then we end up here at something like 10 meters per second. So this is just helping you better understand these motion graphs. Again, we're going to be moving on to kind of the next piece here, looking at velocity from a different perspective. And again, I'm going to take a little bit of a water break, and I'll look out for questions. Okay, no questions. So I'll go ahead and kind of move on to this next concept, which is another way of looking at velocity, which is going to be as a rate. So again, it's not something that we're necessarily thinking about all the time is sort of like, okay, yeah, it's a rate, whatever. But there are tons of rates. And if we understand rates, we're not only going to understand velocity, but we're going to be able to take what we understand about velocity and to extend it out into the future, which is helpful because if I can study one thing and that sets me up to understand, like, I don't know, 5 other things, that means that my future learning is just going to be that much easier. So what was our rate here? Well, it's just something over time. We could put anything over time, really. But in this first one, right, we had was the displacement, or how far, right? That was how far we went, the meters over our seconds, the meters over time. But we could also look at something like flow. So for instance, let's say that we have the volume over time, right? That's going to be a rate as well. So that could be volume over seconds. And so if you think about this first one, right, the greater your velocity, the greater your meters per second, that means that for every single second, you're going to go a further distance. So if we were sort of looking at that here, right, it was going to be 1 step, maybe it's 10 meters, and that was 1 second. Maybe we took another step, and that's another 10 meters, and that was another second. For volume, on the other hand, we're just measuring how much stuff we get at a time differently. So before we were thinking about how far we get each time, and now here, instead of looking at how far we get each time, we're looking at how much volume we get each time. So you just think about like each second, you're going to get a beaker that's filled up. So if this was sort of second 1, this would be second 2, this would be second 3. Let's just say that you got 10 milliliters of flow per second. Basically, what would happen is if you were to take whatever this is and to put it into a beaker, after 1 second, it would be all the way up to the 10 milliliter mark. And that's a Q value for this guy here. Another example of this would be something like power. So this guy is going to be how much energy, joules per second, do you use at a time? So for example, if we're looking at this guy here, right, we could imagine that if you were looking at energy in terms of like, I don't know, a battery. It's not, I mean, batteries are measured usually in volts, but let's just look at it from this energy perspective. Let's say that our power was 10 joules per second. So what would happen is this battery would produce 10 joules, and that would be after 1 second. And if we waited another second, now what we would see is that we got another 10 joules. And if we waited another second, we would again get another 10 joules. And a lot of this stuff obviously is not related to what we have discussed so far, because we're talking about motion. None of this is motion. But we can also see acceleration in the exact same way. Because in this guy here, the way that this works is this is going to be the velocity over your seconds or over your time. So in this case, we're talking about measuring things out in terms of velocity or speed increases. So again, if I was sort of starting here and I started off at 0 meters per second and I go 1 second down the road, what am I going to be at now? Well, let's say the acceleration is 10 meters per second squared. You're going to be gaining 10 meters per second. And if I go another second, we're going to be gaining another 10 meters per second. So in this first scenario, if I wait 2 seconds, how far have I gone? Well, I've gone 20 meters. And if I was looking at 3 seconds with this particular flow, how much volume was totally here? Well, this would end up being 30 milliliters. And in this bottom one for the power, and I was looking at this guy here, and we had 3 seconds, and it was 10 joules for each of these seconds. What would be the collective amount? Okay, well, that's 30 joules. And then in this last one here, how fast are we going at the very end? Well, it was 2 seconds, and we gained 10 meters per second each time. We started at 0, so we're going to be going 20 meters per second at the very end. Hopefully you're seeing that this is a bit repetitive, and I do apologize that I realize that my face is right in the way of what I just wrote. But hopefully you're sort of seeing how a lot of these rates, like, they're the same thing. Yes, different equations, whatever. But if you understand the concept of the rate, you can understand that all of these are rates. You technically know how to solve all of these types of problems that are set up in the same way if you understand the velocity question. And to kind of prove this to you here a little bit, I guess I'll go back to pink, since that's the color I was rocking when we were doing this. We're going to look at some of these other questions and see how it is really similar to that one that we took that pause to come to and solve. So here it says a car starts at rest, then accelerates at a constant 40 meters per second squared. How fast will the car be going after 4 seconds? So all this is sort of saying here is, right, this is your 40 meters per second squared, saying, hey, you're going to get 40 meters per second for every second that you go. That's why the seconds are squared on the bottom. That's what it is to accelerate, to speed up or slow down. Okay, so our car starts off over here. It's got no speed to start off with. 0 meters per second. Okay. In the first second, how fast is it going to go? So we're right here. This is 1 second later. We're going to be going 40 meters per second. Okay, we go another second down the line. We're going to gain another 40 meters per second. Now we're going to be going 80 meters per second. ... We come down. We need to do this for 4 seconds. So how will this sort of math work out? Well, I mean, hopefully this is relatively easy to see. It's the same thing as before. We need to do this 4 times. So we're going to times it by 4. So if we started off and we're going to gain 40 meters per second each time, we are going to gain that 4 times. Then you will be going 160 meters per second at the very end, which is an unreasonably fast rate for a car to be going, but nonetheless. So hopefully this makes sense. We're setting these 2 questions up in the exact same way, despite them looking different from each other. And another person asked, will we be covering torque and tension pulleys in another video in this one? That will be in another video. It's going to be in a forces video, which I'm planning on doing in about 2 weeks from now. Okay, so now let's go and look at the last one. So this one here says, if someone has a heart rate of 75 beats per minute, there's your rate, right? So what we know is that we get 75 beats. And that is going to be in a minute. So if I was to look at a minute, I could chunk this into 75 pieces. And it says, and they eject 70 milliliters of blood each beat. How much blood does their heart eject in 10 minutes? Okay, so again, if we look at each of these beats, so just one, we can define this beat by 70 milliliters of blood right there. And again, this whole thing was 1 minute. So that's 1 minute. And they want to know how many are we going to eject, or how much blood does this eject in 10 minutes? Okay, well, I need to look at times 10 of these here. And again, you may say, okay, right, I haven't memorized a particular equation for this. You could look at something, I don't know, like maybe some of the cardiac output and the heart rate ones, or you could look at something like the Q equals volume over time. But also, we can just look at it this way. We can have this sort of understanding about rates and use that instead. So if I look at this here, I'm going to say, okay, well, I want to know how much blood do I get in a minute? Well, I'm going to have 75 beats. Each of those is 70 milliliters. So if I take 75 and I multiply that by 70, what I'm going to get at the end of this will be how many milliliters I get in a single minute. And then I want to know how long is, or how much do I get in 10 minutes? Well, I need to upscale this by 10 minutes because I don't care about 1 minute, but I care about 10. And if we were to go ahead and do this math out, let's see here. So 7 times 7, that would be 49. In this case, it was actually 70 times 70. So we need to add their 2 zeros back in. Now we're going to go ahead and do 7 times 5. That would be 35, but it was really 70 times that, so it should be 350. So if we add this together, we get 5,250 milliliters. So in 10 minutes, we do 5,250 milliliters. So again, 3 very different questions about 3 different things. And at the same time, what we're seeing in each of these ones is that the concept of a rate, which is what velocity is, can transfer and can help us better understand how to solve these particular problems. So let's go ahead and look at yet another representation about velocity. My hope here is that I'm just sort of presenting it from lots of different angles. So if you get asked about it on the MCAT, you're not thrown off, you're prepared. We're going to put a lot of things together here. So let's imagine that we have this ball and it's been sort of shot out or ejected here. And what we're doing is we're taking pictures of each of these. And this is what we see if we were to line up all these pictures over time. We would see that this was position 1, position 2, position 3, position 4, and position 5. So if I come to my displacement over time graph, let's say that each of these was taken a second. So between these two, there is 1 second. Between these two, this is 1 second. Between these two, there is 1 second. And between these two, there is also going to be 1 second yet again. So if I come here, I can kind of try and do my very best to sort of chart this out. So at the first second mark, so we need 1, 2, 4 seconds. So 1, 2, 3, and then 4. So we haven't gone very far. We still haven't gone very far. We've gone a bit further. We have gone a bit further. And this should have started at the origin. Move everything over. And then we've gone even farther, so it doesn't even really fit on my graph, but something like that. And again, if we come here, we want to think about this from the velocity. What was going on with the velocity? Well, that is a curved line. So we have a changing velocity. So if we want to come and draw a velocity over here, something like that would end up working. Hopefully this is making a bit more sense in terms of this concept of how motion is working. And now we're going to go ahead and we're going to look at acceleration really briefly, because if we understand the velocity piece, we should be able to very easily transfer this over to what's going on from an acceleration perspective. So we're looking at the acceleration component is the change in velocity over the change in time. I sort of already hinted at that, right? It's how this velocity is changing. So before what we were doing is we were saying, okay, if this was 1 second, I was looking at my distance. So if I started at 0 meters, I gained 10 meters, which means my velocity in this case would have been 10 meters per second. If I look at this from an acceleration perspective and I say my acceleration is equal to 10 meters per second squared over this 1 second component, I'm not talking about my displacement change. I'm talking about my velocity change. So if I started at 0 meters per second and I come 1 second later, which is this one jump, I will now be going 10 meters per second. And if I did this for an additional second from the perspective of the velocity, just the velocity, so not looking at the combination, I would have gone 20 meters, and it would be the same thing. I would now be going 20 meters per second. So hopefully you're seeing how that rate piece is sort of coming in. And again, here too, right? Like if we were coming and we were looking at what was going on in this particular scenario, we can see from an acceleration perspective that it was changing. So for something like this, our velocity over time graph would have to be changing. Our velocity is changing as we increment up in time. We started at 0, we go to 10, we get to 20. Well, what does this tell us about our acceleration? Well, in this case, the acceleration was a constant. So if we wanted to just draw here, be straight across. And again, this should make sense because remember, we have this very straight line, right? This straight linear line. Because we have this straight linear line, what is this telling us? This is telling us that we have a constant, whatever the slope is. Now, what is the slope in this case? Before we were saying it was velocity, but this is going to be the change in velocity over the change in time. That's the rise over the run. So this is the rise over the run. Oh, geez, we're back to acceleration. And this is how we can understand the relationship between these graphs if they happen to ask them. Now, there's something a little bit interesting here because we can go in reverse if we want, right? So we've always been going one direction. We've been going from the displacement over time graph to the velocity over time graph. We've been going from the velocity over time graph to the acceleration over time graph. What if we want to reverse this? What if we want to say something from the acceleration over time graph about the velocity over time graph? Well, we can do that. Okay, how do we do this? So in this particular instance, let's think about how do I take my equation that I have and how do I use acceleration to actually go and solve for the velocity, right? Because I want to go from this acceleration time graph and say something about velocity. Okay, well, we have to do a rearrangement here. So if I take a times t, or the change in a times t, that will be equal to the change in v. Okay, so what would that be doing? That would be taking this value here and multiplying it by this value here. And if we look at that, what that ends up giving us is the area under the curve. So if I take this chunk right here and I looked at it for a particular time frame, let's just say it's right here, I would get the area. I would get this particular chunk right here. And what this particular chunk would tell me would be the velocity. Now, it's not any old velocity. Let's put some numbers to this and use the original scenario that we had so that we can maybe have a clearer understanding of what's going on. So let's go ahead and do this for our 2-second scenario. So this would be 1 second, and then finally 2 seconds. And our acceleration was a nice constant 10 meters per second squared. So we have our 10 meters per second squared. So what happens if I multiply these two together? Okay, well, I take the 10 meters on this side and I multiply it by the 2 seconds. What I'm going to get, velocity is equal to 20 meters per second. So when we look at this area under the curve, it obviously didn't give us all these velocities. That's not what we got. What we got was our velocity final. We got the final velocity at the end of 2 seconds. Where are we? If we wanted to find the velocity final for this point in time here, sure, we could have done that, right? We could have just multiplied 1 times 10, and then we would be here. This is the velocity final at 1 second. This is the velocity final at 2 seconds. So you can see that there is this sort of like interaction or this relationship between these two different pieces. Okay, why have I gone through, I think, like so much sort of annoying description of some of this stuff? Well, I think it's because when we look at a lot of the kinematics equations, people, one, have them memorized and maybe you can sort of put them out there, but you can't actually use them. And a lot of people will sort of come to me and say like a tutoring session and ask this question of like, hey, Chris, like, how do I know what equation to use? And I think it's a good question. It's a great question, actually, right? Like if we're going to have these equations memorized, we should be able to use them. But the thing is that it's kind of backwards to me. It's like the understanding of the scenario and the understanding of these particular things should actually sort of solve this question for you. It should help you understand exactly what is going on. And these equations should make sense so that when you look at a scenario and you manipulate all the pieces and parts, that manipulation flows straight into one of the equations here. So let's go ahead and dissect these from a conceptual standpoint, pulling together a lot of the threads that we just talked about to make sense of what we have going on. Okay, so in this first one, what do we have here? We have v final. So this is telling us our end velocity. So what will we be at the very end? And we're going to say that this is going to depend on how fast we were going at the start, right? This is how fast at the start. Well, that kind of makes sense, right? Because if you're going faster at the start, then your end velocity could be faster at the end. Now, a times t, what is this guy here? Well, if we go back, we just looked at a times t, and we said that would be the change in velocity. So what is this particular equation doing? Well, this is actually relatively straightforward. It's saying, hey, your end velocity is going to depend on how fast you are at the start and how much the acceleration causes you to change your velocity, right? We have to be careful here because our vectors, like we talked about at the beginning, are going to matter, right? So imagine in the scenario, you have a ball and it has a velocity like this. The velocity initial is something like, I don't know, 10 meters per second. If the acceleration is pushing in the same direction, then you're going to end up going faster, right? If the acceleration is pushing you in this direction, then the end result will be equal to faster. But if the acceleration, on the other hand, is going to be here and pushing against this, then the end result will be slower. And that's what's going to determine this sort of sign that you end up here, right? So if you're faster, you're going to add these two things together because they're going in the same direction. But if they're going in opposite directions, that sign is telling us that we should slow down. And that's what I was kind of going back to at that very beginning when I said, like, hey, like those signs, they're going to matter in terms of a conceptual piece. It's going to be way easier to understand this stuff conceptually than it is to try and keep track of just pure memorization of these signs. So if we look at this from the perspective of our graph here, right, we have a velocity over time graph. It says that the V final, right, so let's say that we're going to have our V final, so that's going to be where we end up. That's this guy right here, is going to depend on how fast we start. So that would be right here. This is your V initial. So V initial, this guy is your V final, and how much the velocity changes. Well, what is this slope? It's the change in velocity over the change in time. It's telling you how much you changed. And that's exactly what this first one sort of tells us here. So now I'm going to go ahead and flip and I want to look at these next two, which is now going to talk about the displacement or how far we're going. So in these two situations here, this is going to be how far do we get? Okay. So in this first one, what is it going to go ahead and depend on? Well, it's going to depend on how fast we start and how long we spent doing that. That makes sense to me, right? If you're going 10 meters per second and you spend 1 second doing it, you're going to go 10 meters. If you spend 2 seconds doing it, you're going to go 20 meters. If you're going faster, you're going 20 meters per second, and you do that for 1 second, you're going to go 20 meters. So that's what this first piece is sort of saying. Is it saying, like, how much distance do you get because you had a velocity? Now, this is your starting velocity. But we know things can speed up and slow down. And because things can speed up and slow down, that's what this next piece is going to go ahead and account for here. So I'm going to go ahead and expand this out a little bit and take that t squared and write it out as t times t. Okay, well, what do we know? We know that at is the change in velocity. So we can just come and label this first one as the change in velocity. And we multiply by the time. Okay, well, what is this telling us? This is saying, hey, you need to take how much distance you get because you had a velocity to start off with, and you need to add it to the change in velocity, change the time. Well, that's how much distance you get because you change velocity, right? So this whole chunk right here is how much distance because of a velocity change. Now, there's something a little bit weird here. What is with this 1/2? Why do we have a 1/2 in all of this? Now, we make this assumption with these that we have what is called constant acceleration. That means that the acceleration doesn't change. Okay, let's go ahead and look at what that looked like. Right here. Great. Sure, I know these are x and t graphs and v and t graphs, but for the moment, let's just go ahead and sort of fudge this a little bit and say, hey, you're a vt graph and you are an at graph right here. This guy down below, that is what it would be to have a nice constant acceleration. Your acceleration doesn't change. You're at 5 meters per second squared the entire time. What type of graph did this give us for how our velocity changed? Well, our velocity started at 0, and it went and took this nice sort of slope up like this. Okay, cool. So let's say that we started at 0, we add, and then we get to 10 meters per second at the very end. And we're trying to think about how much distance does this give us, right? Like, how much distance do we get? Well, okay, let's say that I looked right here and we're going 1 meter per second. Well, if we spent 1 meter per second, we just 1 second, we go 1 meter. Okay, that's great. But here's the problem. If we wait 1 second, we're not going 1 meter per second anymore. We're going some other thing because we're speeding up, right? So for example, if this was your 1 second mark, and then we come to the 2 second mark right here, well, we should have gone 1 meter, but we end up going 2 meters per second at the end. So we couldn't have gone 1 meter because we must have gone more than that, right? And so that 1/2 is actually saying, hey, we need to take the average. Why do we take an average? It's a triangle, right? So if we go back to this triangle here, when we look at this, like this right here, what do we know about the area under the curve? The area under the curve is going to be representative of the two things that are being multiplied together. Well, in this case, it's v times t. So what is v times t? V times d is the displacement or the distance. So if we look right in here, that guy would be your displacement. Well, it's not a square. It's a triangle. And if we need to find that triangle amount, that is 1/2 base times height. So that 1/2 that is in this equation is accounting for the fact that our velocity is changing. And that's what we see right here. Hopefully this guy makes sense. I know a lot of this stuff you may never have been taught this way in some of the physics things. Hopefully I've pulled together and laid enough of a foundation. So if you do have any confusion or things are not making sense, please go ahead and do put that in the chat so that hopefully you can kind of get things cleared up, because I know that sometimes this stuff is a bit it's new, right? A lot of it is very new. You're not often taught physics from this particular perspective, and so if you have questions, go ahead and pop them in the chat. Okay. So now let's go ahead and look at this last one here. Again, we have how far do we get, and we're going to come and we're going to look at this guy here. This is just an average. All this is doing, this is just averaging something up. How do I know? Because if you want an average, you got two things. You have one thing, you have the other thing. So let's say it's A and B. You do A plus B divided by 2. If you do A plus B divided by 2, you have the average of A and B. Cool. So what are we taking the average of? Well, we're taking the average of the distance that we get. If we assume we had some initial velocity, we had some final velocity, and we multiply by 1/2, we're going to get the overall distance that we would get from these two things. This is essentially the exact same equation here. It's just that in this one, what we're doing is we're not looking at how much distance do we get because of a velocity increase or change. We're looking at this and saying, hey, I started some velocity, I ended some velocity. What do I get distance-wise from each of these two? And you have to average it out because it's obviously changing a little bit between the two. So for this guy, what are we looking at when it comes to this particular graph? Well, we're looking at a displacement graph and how this displacement is changing over time, like this guy here. If we were looking at it, we know that this will end up being the velocity. And so that's why on this particular graph, we're going to be looking at the velocity, multiplying by the time so we can figure out the exact distance that we're getting. And then we account for, in this situation, how much that velocity changed. So that would be more if you've got a curved graph. Hopefully all of this sort of makes some sense. We're going to go ahead and come and we're going to start to look at a first sort of kinematics question. We've got a couple here. We're going to look at it just in one direction. So none of this like you're throwing a ball off of a cliff kind of thing first. Just we're going to throw a ball up and we're going to have it come back down, and what happens? We're going to think about manipulating these different pieces and how this is going to align with our sort of kinematic stuff that we've looked at so far. Okay, so what do? We have a ball. We're going to throw it up. It's obviously going to come up. It's going to stop at some point in time due to gravity. It's going to fall back down. And here's what we want to know. How long did it take to get up to here and fall all the way back down? And we also want to know, when we get all the way to the bottom here, how fast is it going? And we're going to start out with a ball at 20 meters per second. So let's just go ahead and sketch out what's going on. So here's what we have. We have a ball. It's going up at 20 meters per second. And I know that it's going to start to slow down because gravity is going to start to push against it at 10 meters per second squared. So let's just go ahead and sketch this out and just say 1 second passes. Okay, so I start here. I have my ball. It's 20 meters per second. We go 1 second. I'm going to lose 10 meters per second. So now I'm only going 10 meters per second. Now I'm going to go up 1 more second. So now I'm at the top here. How fast will I be going? Well, now I'm going to be going 0 meters per second because I'm going to lose the remaining 10 meters per second that I have. And this would just repeat itself on the way down as well. So I'm going to start at 20 meters per second, go up 10 meters per second, 10 meters per second is lost, lost, lost. And now I'm going to gain. So I start at 0 and then I gain and I have 10 meters per second. And then I am going to gain another 10 meters per second. Each is 1 second. So how long was the ball in the air? Well, it's 4 seconds. So it's in the air for 4 seconds. How fast is it going at the end? Well, it's going to be going 20 meters per second. So this is a kinematics problem, right? Kinematics problem didn't actually use any of the equations to solve it. How could we use the equations to solve this particular problem? Well, let's go ahead and think about what we did and the specific equations that we have. So we have an end velocity. We have the how fast it is at the start. We have the change in the velocity. We also have how far do we get. We can look at how much distance have we covered, right? Because we had a velocity. And we can also sort of look at this and say, okay, how much did we get because the velocity is changing? So what were we dealing with here? We wanted to know how long, and we also wanted to know how fast it was going. So over here, I'm thinking distance doesn't matter, right? We can see that from these particular equations. We aren't really caring how far did we get along this whole sort of scenario. So that's not going to be relevant. Instead, we're going to be thinking about our velocities because that's what it asks, right? How fast, how long? Now, we actually need to break this into chunks because if we want to know how long it took for this ball to go up and then come back down, we would need to know two velocities. We would need to know how fast we ended and how fast we started. And if we wanted to know how fast we were going at the end, we would need to know the time, right? Because we can't be missing more than one thing. So for this type of question, we have to realize that at the very top here, we have this special known value, which will be 0 meters per second. So we're only going to solve, when we use the actual kinematics equation, this 1/2 at a time. We're going to break this into two pieces. And this is because each piece is going to end up being identical, right? The thing up is going to be the same as the thing down. The only difference there is going back to the vector piece, which direction are we doing it? We could think about this in terms of pluses, and we could think about it in terms of your minuses. Okay, so for this guy here, we have the v initial. That's easy. That is 20 meters per second. We have the v final. That is 0 meters per second. We have the acceleration. That's going to be due to gravity. That will be 10 meters per second squared. And this would now allow us to go ahead and solve for the time value using this one here. Okay, so let's go ahead and do that. So v final, that's going to be 0 meters per second, will be equal to 20 meters per second. Now, this thing is slowing us down, which means from a sign perspective, we have to be subtracting or getting rid of this guy here. 10 meters per second squared times t. Now, it's just a little bit of math manipulation. So 20 over here, negative 10 t. I dropped the units just for the sake of doing this math just a little bit more easily. Okay, so t is equal to 2 seconds. So we know that to go from the bottom to the top, this guy right here, that's going to take 2 seconds. And like I said, this other side is identical. So this is also going to take a t of 2 seconds. So there's our time, right? We use the equation this time. It's going to be a total of 4 seconds. Well, how fast were we going? Well, we were up at 0 seconds here, and we want to figure out how fast we were going when we catch it down back or when it comes back down to the bottom. No big deal. Relatively easy to solve. We're going to use this exact same equation. In this case, we have our v initial, and our v initial is going to be equal to 0. We have our time, and what we're solving for is our v final. Let's plug and chug again. So v final will be equal to v initial, that's 0. In this case, we know that we have the acceleration. It's going to go down. It's going to make this thing faster. It's still negative technically because of the direction that it's going. I'm just going to put a positive here, and I'll talk about kind of like why I'll do this, because for me, my sign is always going to be conceptual. I don't tend to solve it just based on the units. I will solve sort of the actual value, and then I'll think about what my sign should be. So then this guy here, what is this going to end up being? This will be 10 meters per second squared, and it's going to be times t now. So it will be 2 seconds. Well, what is this? 20. So the v final will be 20 meters per second, and we know that this will be in the down direction, which was sort of defined as that negative sign. So here you can see, right, I used the more conceptual way of doing it, got the correct answers, and now you're seeing how you can actually incorporate the actual equations and how I sort of picked among these three from these. Any questions? No questions. Okay, keep an eye on the questions. Let's go ahead and look at our next one. So here's what we have, right? We have a car. It's accelerating. It's constant acceleration. It's going to come over here, and its velocity at the end is going to be 30 meters per second. What we're going to see is that we have an x is equal to 60 meters. So from this point A, call it A, and this point B, we have gone 60 meters. And we have a time here of 6 seconds. So we know that to go from A to B, it was 60 meters, and it took us 6 seconds. And at the very end, we're going to end up being at a velocity of 30 meters per second. And here's what we want to know. What was our velocity at the start? So what was our velocity at the start? And what was our acceleration? Okay, to begin with, I'm going to start with my more conceptual understanding of what is going on. So here's what I know. I know that if I look at this, we can divide this 60 meter piece into 6 second chunks. So that's 1 and 2, 3, 4, and 5. So I have 1 chunk, 2, 3, 4, 5, and 6. That's our 6 seconds. This is 60 meters. So if I want to know how much like my velocity is, how much each of these particular chunks is, oh, well, how much did I get in this first 1 second? It must have been 10 meters because I have to do this 6 times and I have to go a total of 60 meters. Another way we could have done this would have just been saying, okay, great, we have our velocity will be equal to the change in displacement, that's 60, over our change in time, that's 10 meters per second. Okay, whoa. This is kind of weird though, because at the end here, we have a v final, and we said that we're going 30 meters per second. How is it that we're going 10 meters per second? That this doesn't make any sense, right? It just doesn't make any sense. If we started at if we ended at 30, how are we going 10 meters per second? Well, we have to be careful here because what we just found, that is the average velocity, right? This thing is speeding up. And what we did is we said, hey, what if I pretend that we're not speeding up, that we just go at one speed the entire time? Because that's actually just easier for me to think about. Well, if we do that, we find the average velocity and we would get to here. Well, what did I say from before? I said that if you take two things, right, you take A plus B, you divide them by 2, you will get the average of something. Okay, well, what if I take the V initial plus the V final and I average it? And I know that value is 10 meters per second because this is perfect because we wanted to know what was the V initial value? What was the VI at the start? Okay, great. Well, I can just figure this out from this right here alone. Relatively easy to do. So if I come here, what was my V initial? Well, I don't know. I want to solve for that. What was my V final? That was 30. I have to divide that by 2. Will be equal to, okay, this has to be equal to 10. And again, we're just doing math. Just going to do some math. So multiply that off. VI plus 30 is equal to 20. Subtract 30. VI was equal to negative 10 meters per second. So what does this tell us? This tells us that before we started accelerating, this car was traveling in the opposite direction that it ends up going, right? This car was like backing up, going negative 10 meters per second until something pushed it this direction and accelerated it until at the very end of this entire thing, it ended up going 30 meters per second. So again, we can sort of use this more conceptual understanding of what's going on to solve the problem. Again, let's go ahead and see if we could use one of these guys to pick out our values and sort of figure out the right answer in this particular scenario. Okay, so what do we know? We want to know how fast this thing is going to go at the very end. We don't know the acceleration, so anything with an acceleration in it is probably out. That means that the only thing that we're really left at would be this one at the very end here, right? The delta x is equal to the 1/2 VI t plus VF t. And we could go in and we could solve this. And again, remember what I said, this is where we were doing the average piece. So if you want, you could use this particular equation. You see how I'm picking it. I'm thinking about what do I want? What do I need? What do I have? And getting rid of anything that doesn't really fit that. And it also matches my more conceptual understanding of what is going on for this particular kinematics equation. Since we're getting on, I'm not going to go ahead and show the resolving of this particular one here, but hopefully that's kind of helpful. You're sort of seeing how this is sort of coming together. The last one I want to go and look at is, what about the acceleration, right? So we need to figure out our acceleration in this particular situation here. Okay, so we know where we were starting. We started out at negative 10 meters per second. And we need to get up to 30 meters per second. And in how many jumps are we going to do this? Well, it was in 6 seconds, so it's going to be 6 jumps. So we need to take 1 jump, 2 jumps, 3, 4, 5, and 6, and end up here. So how do we equally distribute these pieces here into the different components? Okay, well, we could just take the start and the end, right? And we could average it out over these 6 seconds. Okay, cool. So that would be the negative 10 meters per second to the 30 meters per second, and then dividing that by 6 seconds. What is that guy, right? If we think about this from an equation perspective, that's the acceleration is equal to the change in velocity over the change in time. That's all we're doing here. So what was our change in velocity? Well, we went from negative 10 up to 30, so a total of 40 meters per second we had to change to get from here to here. We did it in a total of 6 seconds, and if we do this math, we will get our acceleration in this particular case. So hopefully a lot of this kinematic stuff is making a little bit more sense in terms of how you solve it. A lot of it is honestly using the original sort of like change in velocity, change in time, or change in acceleration over change in time to kind of get as far as you can. And then if you really, really need to use one of the kinematics equations, that's kind of where you would end up going from there when it comes to sort of these different pieces with the equations. I'm going to just check the chat, see if there's anything there. Help me out from a variable acceleration in 3D space. Yeah, MCAT doesn't cover 3D space. We're going to look at two-dimensional motion. So this has been one-dimensional, so we'll get to two-dimensional motion here in a sec. I'm glad you like the channel. Hopefully I'm going to be putting out more regular videos and doing some consistent streams like this guy here. I feel like vectors kinematics is a little bit of a rough one to start off with because it's a little bit hard even for me to understand sometimes. But hopefully we'll get rolling and I'll cover some things that you guys you're interested in. Okay. Let's go ahead and look at one other way the MCAT can kind of ask some of these motion questions. And this is just by stacking variables. So let's say that you have this sort of scenario here and you want to know the force in this case, right? So we're looking, hey, like what is the force, right? Force is equal to mass times acceleration. And what the MCAT's really doing is like, yeah, you think F equals ma, but then they don't give you the stuff that fits. Realistically, all they're wanting you to do is just sort of nest stuff. So when we look at the scenario, what we have is we have a 2 kilogram ball. It goes from 20 meters per second to 40 meters per second. It does it in 5 seconds. Hey, what is the force? Okay, great. So like, how do I find an acceleration in this perspective? Because that's what I really need. Well, right, it's a change in velocity over the change in time. Change in velocity is 20. We go from 20 to 40. This guy is 20. Change in time, that guy is 5. So the acceleration value is 4. We come and we plug this in. So we get 2 times 4. And there is your force. So again, it's just sort of showing you what the MCAT does with some of this stuff, right? What we're seeing in this scenario is not so much on the kinematic side. It's taking something that's a bit simpler and just showing how they'll nest it. We're not covering forces right now. The whole point of this is just to show you that the MCAT can sort of build these things together. So if it's not something that you're thinking about, right? Like you're not thinking about how some of this stuff nests and you realize, shoot, this question, I was completely lost. It didn't fit the mold of what I was thinking. Ask that question when you're doing some of your review is, were they asking me to nest? Were they asking me to see how multiple equations fit together to get to an answer? This is just one example using some of the stuff that we've looked at. Oh, where's my next page? Oops, we put this here. Okay. So far, what we've been looking at is really just things that are moving in sort of just like one direction. So like solely up and down or solely left and right. But what happens if we have this scenario over here where we say like yeet a ball off a cliff, right? We're going to just throw it straight off a cliff. Well, now we're dealing with something that is moving in two different directions. And as one of the people was saying, like, this can also happen in three-dimensional space, because obviously a ball can move in three-dimensional space. So you could imagine that, something gets shoved down and also forward and also sort of like away from us. Now, while I'm not going to cover three-dimensional space sort of questions, really, the two-dimensional stuff is really the same as three dimensions. It's just like you're thinking about doing what I'm about to show you for 2 dimensions a third time. That's really it. Is like, we're just going to be working it out one and then the second one. If you had a third dimension, you would just work that third dimension out. Now here, I'm not going to deal with angles because I've not really seen any questions on the MCAT that deal with angles when it comes to motion in more than a single direction. Okay, so how do these questions work? Well, let's go ahead and just kind of think conceptually about what is sort of going on here. So in this first scenario, what do we have? Well, we have a ball that's going to get thrown off of this cliff. What's going to happen to it? Well, it's traveling 20 meters per second. Let's assume that in this particular circumstance, we do not have any air resistance. So like, there's nothing that's actually stopping or slowing the ball down in the left and right directions. If that's the case, then that means that if this thing could just float, it would go 20 meters per second forward for like forever, until it hit something that actually stopped it. So, right, it doesn't fall. There's no gravity. This thing is just going to go on this way for 20 meters per second, basically infinitely, because nothing slows it down. Now, we know that that's not actually what happens, because gravity causes things to fall to the earth. So if we're looking at what's happening to this ball here, gravity is going to be pushing this thing down. So it's not going to just go straight off. It's going to keep going in this direction, but it's going to start to fall at the same time. And now this is that vector that we were sort of looking at before, right? So if we're thinking about our vector, this is sort of our rough trajectory. So we're going to go down. It's actually going to curve more like this. We can talk about why. There's sort of that vector piece. We're looking at the 2 different components of it, like this here. Whoop, that's the eraser. Which means that at some point in time, this ball is going to hit the ground, and that is going to stop its forward motion. So at this point in time, it is no longer going 20 meters per second once it sort of like maybe hits and rolls to a stop. So really, what stopped this direction, what stopped its motion in that X direction, in the left and right direction, was the fact that it fell and hit the ground. So what does this mean? This means that the direction here, this motion, right, how long this takes or how far you go, this is what is going to stop all other dimensions in this case. Now, the one thing that is always going to be the same between the dimensions is always time, right? Because if you have a ball in the air, it didn't matter how you traveled. If you traveled for 5 seconds, that means you spent 5 seconds going to the right or to the left. You spent 5 seconds going down. And if you had a third dimension, you would be 5 seconds into or out of the page. Because time doesn't really care about what direction you go in. This means that anything that we find out about time-wise can be applied to solve to the other dimension. So if we want to solve something in this left and right direction, we can take the time, maybe we solved it in the Y direction, in the up and down direction, we can apply it there. No big deal. So let's go ahead and look at some of the questions that we can ask now that we have a clear understanding of how 2 dimensions are a little bit different. We want to know how high was this thing that this ball was sitting on? So what we have is a ball. It gets shot off this cliff at 20 meters per second, and it stays in the air for a total of 5 seconds. So it spends 5 seconds in the air. So the first question is, how high was this particular building, cliff, whatever? How far did the ball end up going? So if we measure from here to here, how far did the ball go? And how fast in the X and Y directions was it going right before it hit and it stopped? Let's go ahead and start with how high. Now, this is actually relatively easy because we can take this particular question and turn it into something that we have actually already seen. what we're going to do is we're going to actually ignore the left to right movement, because the left to right movement has nothing to do with falling to the ground. So we're going to take that two-dimensional problem and we're going to turn it into what we just did, where we're only thinking about motion in one direction. So here's what we know. We know that this ball is going to go ahead and it's going to fall like this here. It takes a total of 5 seconds, and it accelerates due to gravity at 10 meters per second squared. Again, I'm going to break this up like I have been the entire time. So what do we know? We know that, okay, second 1, 2, 3, 4, and then finally 5. So in this first one, how fast are we going? Well, we start at 0. We fall, we're going to gain 10 meters per second each second. So we're at 10 meters per second. We're at 20 meters per second. We're at 30 meters per second. ... all the way to 50 meters per second. Now, just like we talked about in that other scenario, we can't just randomly pick one of these values and use it to figure out how far we're going, because we don't know, right? Like, it's going to depend. So what do? We average them, because what the average gives us of all of this is, if we pretend like we just traveled at the exact same speed or the exact same velocity the entire time, what would that velocity be? Well, we start at 0, we end at 50. What's the average? 0, 50, 25 meters per second. If we go 25 meters per second for a total of 5 seconds, what do we get? We go 125 meters. So how tall was this? This was 125 meters. If you want to use a kinematics equation, you can. We can go ahead and we can look at that. Again, let's go ahead and go back to that one and think about what should we pick out here. Okay, so here we are. We want a distance. We want a particular distance. What do we know? We know that we have a time. We know what we start off velocity-wise. And we know as well that what we're going to get at the end of this is it's going to be based off our acceleration. So we should pick this guy in the middle here, right? Because we don't know what the final velocity is. And we do know what our velocity initial is, and we do know what the time is, and that would help us this. This is not going to help us that much because it doesn't actually tell us anything about the distance. So here we've picked out the most relevant kinematics equation that we can use. So that's going to be our change in x will be equal to vi times t plus 1/2 at squared. Let's go ahead and pop back to where we were and use this one. We're going to get the same thing, and we're going to see exactly how this happened in the breakdown. Okay, so delta x is equal to vi times t. What was our initial velocity? Well, this thing was at rest. So that's 0. Now what we're going to get? 1/2. That's that average that we did. Remember when I made this average, that was the 1/2ing right there. A, that's going to be our 10 times t. That's how I got from 0 to 50 right there. And then what are we going to do again? We're going to multiply that guy by 5 again. So you're seeing here my conceptual understanding of this broke it down into the exact same equation we're about to do. We're getting the exact same math. So 10 times, let's see here. So 10 times 5, that right there is going to be 50 divided by 2 is equal to 25 times 5 is equal to 125 meters. So they're showing it both ways. We solved it the conceptual way. We also solved it in terms of the actual kinematics equation that you could use. So we've answered this first question. How high? 125 meters. So now we can go and think about how far did the ball go, right? We want to know in this direction, how far did this ball go? This is actually really easy. This is probably one of the easier questions here. So here's what we know. It spent 5 seconds traveling. It spent 5 seconds traveling just to the right. So if I, for a moment here, ignore, right, the other direction, and I know that it's going to stop after 5 seconds, there's nothing speeding this up or slowing it down in this direction. We start at 20. We do this for 5 seconds. Okay, so what we're going to do is we're going to take 20-meter jumps 5 times. So that's the first jump. That's the first second. We go 20 meters because that's what we get. We get 20 meters for every second that we go. Next second. Now we're at 40 meters. ... all the way through. If we want to do the math, right, this would be our velocity is equal to the change in displacement over the change in time. You multiply these two together, right here. So VT will be equal to the distance. So 20 meters per second times the 5 seconds. We're going to go a total of 400 meters in this direction. Did I do the math right? No, I did not do the math right. 100 meters. Mental math fail. There we go, 100 meters. Okay, so how far did the ball go? 100 meters. Now, how fast in the X and the Y directions were we going when we hit this particular point? This is actually also pretty easy, honestly, in the X direction, because it's just 20 meters per second. Because remember, there's nothing speeding it up or slowing it down. So that is going to be 20 meters per second, 20 meters per second, like I said, for infinity until it actually gets stopped. So right before it hits, before it actually slows down, in the X direction, so the Vx will be equal to 20 meters per second. Now, what about the Vy? Well, again, we can just think about this in the single direction. So we're going to come back to our X and our Y page, and we're going to go ahead and think about what did we have here. Now, I happened to just go ahead and chart this out, right? Like I just charted it out, and we can see, we can just pull this here as a 50 meters per second. Now, how could I have solved this? I want to use an equation. Okay, well, what do I want to know? I want to know, what is my velocity final? What's that equation? It's velocity final is equal to velocity initial plus AT, right? How fast you go at the end will depend on how fast you go at the start, adding in how much you speed up. The initial velocity, that's nothing. AT, cool. A is 10 times T, 50, just like we solved there. Now, is the MCAT going to ask you a question like this? No, it's multi-part. Why did I bother showing it multi-part? Why have I bothered showing lots of these questions multi-part, in fact? Because what I want to do is I want to try and prepare you the fact that what the MCAT does is it just remixes a question. It shows it from one angle. It shows it from this other angle. So now you've seen it from lots of different angles. You've seen the various different versions that they could potentially sort of throw at you. And hopefully this sort of helps you have a better understanding of some of these kinematics equations. That went a lot longer than I thought it was going to go. It's fine, 2 hours in, but hopefully that was helpful. I see there was one question about, what about the fourth dimension for kinematics? I have no idea. I don't really know how to think about that. I can think about it in 3 dimensions, but not fourth. I'd probably have to do some research and think about that. I feel like the fourth dimension is usually time, so I'm not really sure how to think about a fourth dimension since the time is sort of already there. But yeah, hopefully that's helpful. And there'll be more lives to come. I'm thinking of planning them about every 2 weeks. So the next one I'm hoping to do is going to be forces, wanting to kind of finish up a physics series here, kind of going through all of the material from start to finish and kind of teaching it in my style. It'll be a little bit hard if you don't watch kind of all of them because it will build on top of it, but hopefully I'll find a way to make them sort of like jump into a bowl. But that's really it for today. That was kind of my one stream coming back after a little while. Hopefully people enjoyed it, got something out of it, and hope to see you next time.